How's it going, Bruce? Feel free to ask me questions if you have them while we wait. What else now? Hopefully the test went well for you guys today. Hope you all did really well. I haven't looked at the grades yet. Haven't had a chance. Good deal. It does look like the class average was quite a bit higher than I'm used to. Like normally our first test has an average somewhere between upper 40s and lower 50s. Maybe sometimes it's 55, 56, something like that. Uh, but I know the two classes that took it already, they both had averages in the upper 60s. So hopefully y'all had something similar. I'm sure you did because you're awesome, right? Y'all can, we still have another minute, so you're welcome to ask me any questions you might have. Wouldn't ask me anything specific about the test. Well, never mind. It looks like everybody did take it. Actually still no, because I have a similar test for my face-to-face 242 class. Oh God, y'all did really well. Good job. But I did have a similar test for my 242 face-to-face class, so I'd hate to uh, tip your hand to, and y'all mentioned what we did on the test, and then someone has to make it up this week, not actually, or get an advance from doing it. Is that Mariana that just I think it's Mariana that just signed in? You can chat yay or nay if you don't mind. I'm just trying to check roles so I make sure I have the right names.
It's Sebastian. I don't know why
Oh, gotcha.
I'm just I'm just S, but
You got superpower and now you're like Superman. Gotcha. So that was not the S I expected. Thank you. I appreciate that. All right. Well, it looks like time for class to begin. I'm looking at the statistics right now. It does look like the class average was 75. Good job. Y'all ripped it. Awesome. Uh, that's a really high class average for the first face-to-face test. I did try to make it not too terribly hard, but I also didn't make it too terribly easy. So by all means, if you guys scored over the normal mean, which is, you know, low 50s, then you can take some solace in the fact that you did pretty well, even if that's lower than the mean this time. So still, keep your head up and we'll be able to do great things the rest of the semester. Well, time is has reached us. It's time to actually go ahead and start. So I'm going to go ahead and get started. Uh, what I can tell you is that last time we ended up finishing by computing that CP minus CV for an ideal gas was actually equal to R. Now we can go on from that and find out what CP and CV are specifically for an ideal gas. And that's what I'll first start off with. Oh, I turned my iPad off and I thought I left it on. So we can start off with that. CP minus CV is equal to R. And basically, what you recall is when we did the specific heat at constant volume. Again, this is molar specific heat, so it's capital CV. We got capital CV is equal to, well, we got capital CV. Actually, I'll just write it down. I was trying to do it in such a way that I could just lay out a picture it, but I know sometimes that fails me, so it certainly fails you guys occasionally. Uh, so it's probably better that I go ahead and just show you. So what we found last time, if I kill some of these windows, was that CP, and I'm going to share the screen with you now. Finally, my iPad's on, so I'm excited. Okay, so that should pop up any second now. There it is. So what we found last time, if I look in my notes, you'd see that CP minus CV is equal to R. And remember that CP, for instance, is the same thing as the molecular weight times CP, and CV is also the molecular weight times lowercase c, lowercase v, where those specific heats in lower cases are like calories per mole Kelvin, or excuse me, calories per gram Kelvin, or calories per kilogram Kelvin, or joules per kilogram Kelvin. Okay. But what we also had found out was that you can actually use some of these principles. For instance, we can take Newton, or excuse me, take the first law of thermodynamics, which says dE internal is equal to, actually, I don't want to do it in the differential form. Let's go ahead and take it back to the macroscopic form. So delta E internal, according to the first law of thermodynamics, is Q minus W. And remember, Q means heat added to the system. And if you have heat taken away, that's a negative. And W means heat work done by the system. And if work is done on the system, that's a negative. So we can actually take this and realize that, in fact, QV, excuse me, we can realize, in fact, that CV, if we take QV, oops, there it is. If we take QV is equal to N CV delta T, and then we can realize that that looks a lot like our internal energy. Specifically, the internal energy is equal to 3/2 in RT. Then you can compare these two, because QV equals NCV delta T. You can compare the two, and you see that, in fact, 3/2 nRT is equal to N times CV. And actually, in both cases, it should be delta T. So I'll put a delta there, and let me clean that up a little bit. Sorry about that. 3/2 N R delta T is equal to N CV delta T. And that's what we're shooting for here. And I can fix that now with the delta T. And what you see is clearly this N and this delta T drops off of this N and this delta T. So we're left with CV, the capital version, is equal to 3/2 R. So if I plug that in, CP minus 3/2 R is equal to R. In other words, I'm plugging that CP into this. So those two equations combined give me what I have here. Then you can see that CP, the capital CP, is equal to 3/2 R plus 2/2 R, which would be 5/2 R. So now we have the full expression. CP is equal to 5/2 R, and CV is equal to 3/2 R, and CP minus CV is equal to R. So those are our new expressions we found. Darn it. Those are our new expressions we found. And with that, we can define another quantity that's going to come in handy. And the quantity we're going to define is gamma, which is defined to be CP over CV. And if you put in the 5/2 R over the 3/2 R, you see that you end up getting 5/3. So that's another value. Now, you don't necessarily know why that value is important, but that's to come. So it turns out that if you wish to take these results and run with them, then we can do some computations specifically regarding not only the equipetition theorem, which we've already talked about to some extent, and solids, which we somewhat talked about already. We can actually go to consider an adiabatic expansion. So let's do that. So for an adiabatic expansion, and it doesn't necessarily have to be an expansion, it can be a compression. The main thing is we're just considering a change in volume for an adiabatic process. What we know from the first law of thermodynamics is we can write dE internal, and now you see why I tried to write the differential version a second ago. dE internal is equal to d bar Q minus d bar W. Okay. Now, if we actually consider the adiabatic process, then this becomes, since it's adiabatic, dq is equal to 0 because adiabatic means q is equal to 0. So if we actually don't allow heat in or out of the system, then we get dE internal is equal to negative d bar W, which we can also write as negative P delta V, or excuse me, P dV. I don't want to write delta V. So I can write that as negative P dV. And from that, we can put the two sides together on the same side of the equation, and we get dE internal plus P dV is equal to 0. Now we can go ahead and introduce some things like, for instance, we know that dE internal, which we found this last time, is actually equal to NCV. In this case, we're going to say dt. So that's equal to NCV dt, which is basically the same thing that we used up here. So I'm going to say, let's see if I can do it this way. So this stuff right here, that's where this came from. Okay. So now when we do that, we can go about making this a little bit neater by saying dE internal, which is going to be NCV delta T, or in this case dt, and then plus PdV is equal to 0. So that's pretty nice. That has some stuff that can help us. But we can also use the ideal gas law. And the ideal gas law, of course, says, I usually write it lowercase p, uppercase V equals N RT. And from that, we can actually reach the conclusion that basically, if you took the differential of each side, you would get P dV plus V dP, that's the left-hand side, is equal to NR dt. Okay, so we can combine those to give us a slightly new expression that we can actually make into a differential equation. So what I can do is, let's see, I want to take PdV, I've got that one. I've got VdP, I can do that one. NR delta T. So what I'm going to do is I'm going to take this first expression, which is just dt. So the dt, according to, in this case, I'm talking about this expression right here. Okay. So if I take that dt and solve for it, I get P dV plus V dP, all that divided by N times R. So now I can actually do that and replace the delta T in this expression right here. So when I do that, I get NCV times, now I'm going to say PdV plus VdP over NR plus PdV is equal to 0. And you can see that this n cancels out with this n right here, and that gets us a little closer. Now, you don't necessarily know where I'm going with all this, but that's sort of the whole point, is ultimately I'm going to get something that makes it a little easier. So what I can see right now is I can multiply through by R. Let's see. No, I don't want to. Yeah, I'll multiply through by R. So if I multiply through by R, then I get R. Oops. I wanted a different color. Then I get R multiplied by both sides. I'll put this in red so you see what I'm doing. Times R. And then this times R just gives us nothing. So when I actually do that, you can see the R hits that first term on the left and just makes the rest of it disappear. So I end up getting CV times PdV plus CV times VdP. That's the two terms that were all in one parenthesis earlier, but once I multiplied by R, the R in the bottom canceled out, so I was just left with those terms. But now I will have plus R times P times dV. And all that's equal to 0. But I see I have a common term with dV in it right here. So I'm going to group those two guys as common terms. And what I get is CV plus R times, in fact, in both cases, we have PdV. Darn it. And now that takes care of, for instance, this term and this term. So all I'm left with now is CVdV, or CVV-dV. So now I can say plus CVV-dP is equal to 0. Now, finally, what I want to do is I'm going to multiply through by 1 over CV. So we'll do it like this. I'm going to say 1 over CV, 1 over CV. And when I do that, you can see that on this side, I'm going to get CV plus R over CV. So that's going to become CV over CV times P dV plus R over CV times P dV plus V dP is equal to R. Is equal to 0, excuse me. So now I've got a CV over CV. That clearly cancels out. So this guy is canceling out with that guy. And I got a PDV and another PDV. So I can actually combine those two. And PDV times 1 plus R over CV times PDV. And in so doing, actually, no, I don't want to cancel the CV, did I? I think I dropped a CP somewhere. Thought I had a CP. Oh, I can make it with that. Okay. Gotcha. So I'm going to take and just copy this formula. So I'm going to do this. And I'm going to do copy, go to the next page, put paste in. Okay, now that I have that, I can say basically, let's not actually cancel out that CV. So ignore that little step that I did, because I think I want to keep it because I want to do, and actually I make that a lot smaller to do that. Okay, so what I'm going to do instead is I'm going to take the top, which would be C. Sorry about that. I kind of lost track of what I was doing. It's going to be CV plus R over CV times P dV plus V dP. Now, the reason I did that is because we know that CP minus CV is equal to R. So if I take and solve for CP, I get CP is equal to CV plus R, which is exactly what I have on top. So now I can write CP over CV times P dV plus V dP, and this was equal to 0, so this is still equal to 0. And that's really what I was shooting for. I needed this specific differential equation, and I've already made the definition that gamma is defined to be CP over CV. So I can go ahead and call this, for a final step, gamma times P dV plus V times dP is equal to 0. And what I'm going to do is integrate both sides of this. But before doing so, I need to go ahead and get the P variable with the dP, and I need to get the V variable with the dV. So what I'm going to do is multiply by 1 over PV on both sides. So 1 over PV, 1 over PV. Of course, multiplying by 0 again gives us nothing. But in this case, I get gamma dV over V plus dP over P is equal to 0. So now I can integrate both sides. And when I integrate both sides, I also integrate 0 if I wanted to. But the main thing is ultimately we're going to integrate this and get constants of integration, which I can put on the other side. So this becomes gamma times the natural log of V, gamma times the natural log of V plus natural log of P. And basically you'd have plus an integration constant plus another integration constant. I can add those two constants, make a new constant, and then put it on the other side, and it'll be a negative of that constant. So I'll make that yet another constant. So I'll just say all this is equal to a constant. And that takes care of the basically the part I have. Now, what you can also see is, remember your rules of logarithms, and your rule of logarithms says that when you multiply a natural log times a number, that's the same thing as raising the argument of the natural log to the gamma power. So now I can say ln of V to the gamma plus the natural log of P is equal to a constant. And then from that, I can realize that the sum of two logs is in fact the product of the logs. So I can now say the natural log of P times V to the gamma is equal to a constant. But the beauty of a constant is, again, it's just a constant. We can make it anything we want. So I can actually raise both sides as exponents on an exponential. And of course, the exponential to a constant power is just another version of the constant. So I end up getting, in fact, the ultimate response, which is P times V to the gamma is equal to a constant. And this is the result that I went after. This is true for an ideal gas, and it's specifically true for adiabatic process that is quasi-static. So true for a quasi-static adiabatic oh, that's not supposed to be I just dotted an A. Adiabatic. Make this a little higher there. Ideal gas. Okay, so that's the conditions under which it's true. Anybody have any questions on that? I mean, it's a lot of work for that one thing, but that's really not a lot of work compared to what you normally do in an engineering or a thermodynamics engineering or a physics class for thermodynamics. Both of those classes, which are normally what you take if you become a physics major, for instance, uh, in some cases, you'd have 5 chapters would put together to make a 2 semester course. And other courses, for instance, in thermodynamics, these chapters 17, 18, 19, and 20 would be a thermodynamics course, and but a much higher level. So you sort of have a higher level of learning that you'll go to at the junior and senior level years. So you'll get more of that, but basically this calculation is a more trivial version of what you do in those classes. Because in those classes, you'd be required to do a lot more algebra, a lot more derivatives, a lot more integrals, that sort of thing. But the main thing is we got the result we wanted, and we're done with that. So now we can solve a problem. So let me give you an example. This will be example 1. So example 1, what we're going to do is imagine an ideal monatomic gas is compressed at point A in the PV diagram. I'm going to draw that diagram for you in a second. In the PV diagram, where the pressure at A is going to be 200 kilopascals, and the volume at A is going to be 2.00 cubic meters. And the temperature at A is going to be 300 Kelvin, which I'll call 300 with a decimal point so we can use all 3 sig figs. The gas is first compressed adiabatically. God darn it. Compressed adiabatically to state B. B, where PB is equal to, let's say this is going to be 400, decimal point again, kilopascals. The gas is then further compressed to state C, where the volume at C is equal to 0.500, and I'm going to say that's cubic meters. Ah, darn it. Really hate it when that happens. So the gas is then further compressed to state C, where VC is equal to that, and this process was isothermal. Okay. So what I want to know is A, what is VB? And then part B, I would like to know the total work done. Equals question mark. Okay, so let's start off by drawing our figure. So I'm going to give you a P versus V diagram. And this is going to be the pressure axis. This is going to be the volume axis. And what we're supposed to be going from is, let's imagine, for instance, that this right here, let's do this in red. Let's say this right here is point A. And from point A to point B, which is right here, that process is going to be adiabatic. Turn it. Okay, and then it's going to go from there to point C, and that process is the isothermal one. So this is called an isotherm. So the actual bar is called an isotherm, the actual graph, and the actual graph is called a adiabat. And in this process, I want to point out that this number right here corresponds to everything we know about VA, about A. And of course, that means VA is 2.00 cubic meters. And then part B, that's VB, which equals question mark. We don't know that, but that's what we got to do for part A. I mean, for part A of the question. And this right here is VC. And actually, I don't even want to write a VC there. I'm going to write the actual number. And that VC is 0.500 if my memory serves me. Yes. Ah, darn it. And again, oops. So that's that. VB is what we're looking for. Now we also know the other values, like we might know, for instance, the pressure at B, and I look back up at the question, and sure enough, we did know the pressure at B. It was 400 kilopascals. So I'm going to put this in kilopascals for that. VA, the pressure at A, excuse me, PA, is 200. So I'm going to call this 200 and put a decimal after it. And then the pressure at B is 400. And I'll put a decimal after that. And then the pressure at C is, I got A was 200 kilopascals. I got B was 400 kilopascals. And yeah, I wasn't given a pressure at C, but I do know that the temperature for this isotherm was T equal, was it 300 Kelvin? No, A to B. So here I had TA is equal to 300 decimal point Kelvin. I think that was the only place I really knew the temperature. Looks like I got everything written down now. All right, so here's our solution. Anybody have any questions about what's going on here? I know it's a lot going on with this one problem, but we're trying to make up a pretty robust problem so that you can have experience with something a little bit harder than normal. At the same time, it needs to show you sort of all the bells and whistles. So we'll start off with part A, where it's asking us to find what the volume at B is. And we just finished deriving a formula that we can use to actually find the adiabatic, in an adiabatic process, how pressure and volume are related. So the way we normally implement that is we'll say PA VA to the gamma. Notice I'm just using this expression right here. P times V to the gamma is equal to a constant. So PA V to the A, or VA to the gamma, is equal to PB VB to the gamma power. And gamma, good gosh, I've been writing on the whole edge of the paper all this time and not realizing it because I had zoomed in. Gamma is equal to 5/3. Okay. So with that in mind, I can now say that PB is equal to PA times VA over VB. All of that will be to the gamma power. So I'm going to write in PA, which we said was 200 kilopascals, times VA, and VA is 2 cubic meters, over VB, excuse me, over, maybe I did want the, oh no, I didn't want pressure. I wanted the volume to be, darn it. I'm sorry. For a second there, I thought I was solving for PB, not VB. So I did want VB. So let me basically start over. It's not that big a deal. What I can do is I want to solve for VB, so I'm going to raise both sides to the 1 over gamma power. Yeah, 1 over gamma power. So let's do this. I'll say raise this to the 1 over gamma power, and then I'm going to do this to raising it to the 1 over gamma power. And when I do that, I'm going to get PA to the 1 over gamma times VA is equal to PB to the 1 over gamma times VB, the 1 power. That means that VB will actually equal VA times, now I can see that it's going to be PA over PB. All that we raise to the 1 over gamma power. So I can see that VB is going to be equal to the pressure, or excuse me, the volume at A, which is 2.00 cubic meters, times the pressure at A, which is 200 decimal point kilopascals, over the pressure at B, which is 400 decimal point kilopascals, all that raised to the 1 over gamma power, which is 1 over 5/3. So what you're basically going to do is you're going to take 2 divided by 4, which is obviously 1/2, and you're going to raise that to the 3/5 power. And I use parentheses. So I'll put, for instance, 0.5, and then I hit my caret symbol, which is a key that looks like this. But you might also have a key like this or a key like this. Any one of these 3 buttons will do this. And what I'm going to do is I put 0.500, and then I hit the caret key, and then I hit parenthesis. Well, actually, I can make it a little smaller. I hit parenthesis, and then I did 3 divided by 5, and then I did parenthesis again. So that's actually what I'm going to do, just in case you're not that familiar with doing what we're doing here. So I'm actually raising it to the 3 divided by 5 power. And that gives me, now that y'all have seen that, I'm going to erase it real quick. Okay, so now what I have is equal to 2.00 cubic meters. Now notice the units canceled out. The kilopascals and the kilopascals canceled each other out, and I just get 0.65975. Now, I only had 3 sig figs there, and in fact, you might even argue, because Giancoli thinks it's would call that an ambiguous number. You might actually think I only have 1 sig fig, but I'm going to treat that as if it's 3 sig figs, in which case me carrying these extra 2 digits is very, very good. You need to always carry at least 1 extra digit in intermediate calculations. So now I'm going to take that and multiply it by 2. and that'll give me the volume is 1.3195, and the units come out to be cubic meters. So our first answer is VB is equal to 1.3195 with two extra sig figs. So that's technically 1.32 cubic meters is the answer that you would report. But I'm writing extra sig figs just in case we need that for a subsequent calculation, which we probably will. Okay. So that was part A. Does that everybody follow what we did there? Anybody have any questions about that? All right. Now we got to do the work. Okay. So what we're going to do is the work total. Actually, shouldn't be writing in that color. We'll say work total. God darn it, not supposed to be that color either. Work total is equal to the work from A to B plus the work from B to C. Okay, so I'm going to start off with doing the work from A to B, which is an adiabatic process. And I actually locked myself in with a little arrow notation, so I should probably stick to that. But that's going to be work equals the integral of P dV. That's the way you compute work. Now, because we have this wonderful expression for adiabatic expansion or compression, we can say that P V to the gamma is equal to PA times VA to the gamma, where P and V are anytime later. So this actually allows me to solve for P in terms of V. So I can say in this integral, it's going to become the integral of PA, which is just a constant, and then times VA, which is just another constant, and then it's going to be dV over V to the gamma. Okay, so continuing, W from A to B is going to be PA VA to the gamma. Now, when I integrate dV to the gamma, or dV to the negative gamma, then what I'm going to get is negative gamma plus 1 on the bottom times V to the 1 minus gamma power, and that's going to be evaluated from VA to VB. Okay, so when I do this, I get PA VA to the gamma. All that's going to be over 1 minus gamma, and then that's going to give me VB to the 1 minus gamma minus VA to the 1 minus gamma. So that should be able to be done that way. Now let's go ahead and put in our numbers. I've got PA, which is 200 kilopascals, so 200.0 kilopascals times VA, which was 2 cubic meters. And all that's going to be raised to the 5/3 power, because that's what gamma is. And all this will be divided by 3 over 3 minus 5 over 3. In other words, I just took the time to go ahead and get a common denominator and called the 1 3 over 3. Now, this is also going to be VB. Now, what we found VB to be was 1.3195. So here's where we're making use of the extra sig figs. That's going to be raised to the 1 minus gamma power. As we can see, 1 minus gamma is 3 minus 5 over 3. So that'd be negative 2/3. Darn it. So that's going to be raised to the negative 2/3 power minus VA, which we found was 2.00 cubic meters. and that's also going to be raised to the negative 2/3 power. And computing all of that is not that pretty, but we can see what happens. This is going to be 200 e to the third, because it's kilopascals, so it's going to be 200 e to the third times, now I'm going to say 2 raised to the 5/3 power, so I'll do parentheses 5 divided by 3. That's partly why I showed you the other part before. And then I'm going to divide that by 3/3 minus 5/3 is negative 2/3. So I'm going to divide that by negative 2/3. So what I get here is 634,960.4 divided by negative 2/3. And that part of the answer is actually going to be a big nasty mess. I'll write it right here. So this part of the answer is going to be negative 952,440.6. That's way more than enough digits, but anyways, that's what it is. It's a really huge number. And now I'm going to take that 1.3195 and I'm going to raise that to the negative 2/3 power using parentheses again. And that's going to give me, in parentheses, that's going to give me 0.83124. And that is meters. Notice I'm raising the meters to the negative 2/3 power. So that's going to become meters to the negative 2 power. And the units up here became pascals. So the red number has units of pascals times over meters to the second power. So that's the units of that little red boxed off number. Now I'm going to do 2 raised to the negative 2/3 power. And with that one, I get minus, I get minus 0.62991, and that also will be meters to the negative 2 power. So basically we're getting pascals divided by square meters. I think that works. Actually, no, that's to the 5/3 power. So that's actually a positive. That's actually a positive. I'm looking back at this unit here. I've gotten the number really well sized, but the problem is this meters cubed. I put it in the bottom because I thought the exponent was negative, but it wasn't. So this is a this is a 6. And then what the units turn out to be is pascals times meters to the 5th. So this would be pascals meters to the 5th. Okay, so pascals meters to the 5th divided by meters squared is going to be pascal meters cubed. And of course, pascals are newtons per square meter. So when I multiply it by meter cubed, I get a Newton meter, which is a joule. So now I'm going to do 0.83124 minus 0.629961. That part gives me 0.20128. So this right here is 0.2012807 meters to the negative 2. And now I'm going to multiply that by that big, awful 952 number. So I'm going to take that and say times negative 952,440.6. And that gives me negative. I'm just trying to make sure I got everything negative properly. So I did 8 minus 0.6. That should have given me a positive. I did the positive, and then 3/3 minus 5/3 gave me the negative. So this actually gives me a negative 1.9171 times 10 to the 5th joules. So that's the work that's actually done there. I don't know why it came out negative. Let's see if we can find a mistake on there. Anybody see anywhere I might have made a mistake? So the PAVA to the gamma that came out in front, that's not a big deal. dV of gamma to the V to the gamma, V to the negative gamma is what we integrated. And you have to add 1 to that exponent when you integrate. So that's going to, and then divide by it. So that's negative gamma plus 1. That's what we see in the denominator. And then that becomes V to the gamma, V to the 1 minus gamma power. I've got that. Then I'm supposed to evaluate that at VB and VA. So the VB comes first and then the VA comes second. And my VB was supposed to be 1.31. And that's to the 1 minus gamma power. And then my VA was 2.00 cubic meters, and that's the negative gamma power, or 1 minus gamma power. So that all looks right. And then I had 1 minus gamma. So that's 3/3 minus 5/3, which is negative 2/3. So that's basically negative that gives me there. So I don't know why that came out negative, but it definitely does. So, oh, okay. In this case, I know why. There should be a positive sign put on this. So I'm going to put the positive right here because really what should have happened is there should be a negative there. 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 And there should be a negative here. And there should be a negative here. And the reason why is because work is equal to the integral of PdV, but in this case, it's actually a compression. So you're actually working against that pressure. So it should have been the negative of the PdV instead of the positive of the PdV. So that makes me feel a little better. So we're going to call that 1.91 times 10 to the 5th joules. Now, sorry for that delay. Now we can do the other part, which will actually be really easy compared to that. So the work from B to C is equal, since that's an isotherm, we've already worked that out. That turns out to be N times R times T times the natural log of the final one, which would be VC, over the initial one, which would be VB. So that's the formula. You can look that up in your book, but you can also see that I derived that in the last class. So the main thing is that we're going to do is we're going to plug in all these numbers. And I'm trying to remember. So I got you. And by the way, that's at the temperature TB, which the temperature at TB, did I even give you that? I don't think I did. Did I give you the temperature at B? I did not. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at B. I did not. I did not give you the temperature at but we can figure it out. Ah, that's okay. Okay, so this is the temperature at TB. I realize what I'm going to do now. Since it's an isotherm, it's the temperature at B or the temperature at C, which is fine. But remember, the ideal gas law is PV equals nRT. We also know the ideal gas law. I'm going to write it up here in the top left. So the ideal gas law, one thing says PV is equal to nRT. So N times R times TB is the same thing as P times V. And that might confuse you because clearly P and V are changing. But remember, the ideal gas law also has for an isotherm, for an isothermal process, we can say that N1R T1 is equal to N2R T2. So they're identical because they're isothermal, but that also means P1V1 is equal to P2V2. So we can use either PBVB or we can use PCVC to replace that NRTB. So in doing that, I'm going to say this is just going to be P times V. And since I happen to know PB and VB, I'm going to put a B on it and call it PB times VB times the natural log of VC. Now, in this case, VC we found or was given to be 0.500, darn it, 0.500 cubic meters. That's not going to matter though, because we're going to divide it by the volume at B, and the volume at B was what we solved for, which is 1.3195. So that's cubic meters as well. And then the P, of course, is going to be 400 kilopascals. And the VB is going to be the same as it was there. So what I'm going to do is I'm going to take 400 e to the 3 times 1.3195 times, now I'm going to type in the natural log, and I'm going to do that of parenthesis 0.5 divided by 1.3195 close parenthesis, and all that gives me is, of course, the same thing we did before. I forgot to do it again, but basically I was supposed to get a negative of this pressure, because again, it's compressing. So I'm going to put this in here, get it back in purple. And when I compute this, I get positive 5.1218. And that gives me the 2 and the 1 and the 8 as not significant figures. And the units are pressure times volume. That gives me joules, and it's 5.1218 times 10 to the 5th joules. So that gives me that, and therefore the work total is equal to 1.9171 plus 5.1218. Notice they're both the same power, so I'm just adding the mantissa portion of the scientific notation first, and that gives me 7.03. So the answer is 7.03 times 10 to the 5th. Which you could say times 10 to the 2 and call it kilojoules if you wanted. But the main thing is we now have the final answer. Okay. Sorry about the hemming and hawing and the negatives that I had to put in after the fact. But again, because this is a compression thing, we're calculating the pressure of the gas. We're actually having to overcome that. So you can sort of think of it that way if you like. But anyways, that's not only a good solid example, it's very much like the example in the book, which was example, let's see if example 1915. So this one's like example 1915. In fact, it's identical except I changed the numbers. So anybody have any questions on that one? I know that was a lot. Sorry about that, but that's a typical problem when you're working with ideal gases and thermodynamics and stuff. All right, so I promise you that was the last of the most complicated stuff for chapter 19. The other stuff is actually really, really quite easy and actually quite sensible. So after that section, which was 1909, we go into 1910, which is talking about heat transfer. So let me stop for a second, stop sharing my screen. So when you transfer heat, heat is transferred, we'll learn in the next chapter, chapter 20, basically heat flows spontaneously from a warm object to a cold object. Now, if those two objects are touching, then heat can flow by conduction. What I use to remind myself of that is the conduction. The duck part sounds a little bit like touch. Okay, it's not that good. I'm not saying it's a great mnemonic, but it works. So, anyways, conduction, think touching. So when a warm block is up against physically touching a cold block, then heat will spontaneously flow from the warm block to the cold block, and that's a version of the second law of thermodynamics. However, if you have, for instance, a hot block at the bottom of the water, say you have a bowl of water or a pot of water, and you put a really, really hot piece of metal in the pot, you drop it to the bottom. What's going to happen is that piece of metal at the bottom is going to heat up a little wafer or slice of water all around that particular chunk of metal. And that water right there is going to be warmed up. And since it warms up, that means its temperature went up, so its volume went up, and therefore it was the same mass. So the density went down, and that made it a less dense bit of water. So that water would flow up to the top. And then the other water that was not touching it will fall into its place. And then the same thing will happen again. And that circulation type process where this water that's warm can come to the top and then even give its heat off to the air in the above, that's convection. That's basically the same method that your air fryer does. So for instance, if you have an air fryer, which is kind of popular right now, or if you've been to 7-Eleven, you see they have air fryers there. And some time ago, we started getting baked potatoes that could come out really quickly instead of the 45 minutes or something they used to be. That's because of air fryer as well. So with an air fryer, you've got radiative heating, heat going through basically air or even a vacuum is radiation. You also have some conduction. So everywhere, for instance, the potato touches anything hot or metal are conductive, which includes the air, which is not that conductive, but it also includes the bowl of your air fryer, for instance, if that's in contact with the potato, or the rack, if that's in contact with the potato, all that heats by conduction. And then by blowing air through there, that actually allows convection to take place too, so that you sort of get the hottest air against the cold object that needs to be cooked over and over and over again. So that's your first two types of heat. Heat by conduction requires touching. Heat by convection requires a fluid that can basically be circulated. So it can give off its heat up at the top, and then it condenses and falls back down, and then expands again, goes up, goes to the top, can give off its heat again, and then it condenses, falls back down. And I'm saying condenses just to mean that it's getting a higher density, so it sinks back to the bottom again. And then the third way is radiation. And radiation, you'll learn later this semester by chapter 30, you'll know that basically radiation is an electric field waving up and down, say, that this is for what we'd call vertically polarized radiation. It's an electric field oscillating in one plane, I'm going to say vertically, and then that would be called vertically polarized waves. And then at the same time, there's a magnetic field oscillating to the right. Okay. And in fact, there's a right hand rule where if you hold your right hand like this, if you point this finger in the direction that the electric field is positive, which is up, and you point this finger in the direction in which the magnetic field is positive, which I'm going to say is to the right, then your thumb points in the direction that the wave is traveling. So you can see that an upward electromagnetic field going through zero, higher, 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 reaching a max, then lower, lower, lower down to zero. That particular part is the electric field going from zero to a max back to zero. At the same time and in phase with it, the magnetic field will go from zero up to a max at the exact same time as the electric field's a max. The magnetic field will be a max to the right, and then it'll go back down to zero at exactly the same time that the electric field went to zero. That gives you this direction like this. So there's your electric field, there's your magnetic field, and then you see that the thumb is pointing to you, so that's the direction that the wave is actually propagating. We'll be able to show you that that's exactly what radiation is by chapter 30, and actually we'll show little bits of it before then. And it turns out that all radiation that we call electromagnetic radiation is of that form. And what are those forms of electromagnetic radiation? Well, I have a mnemonic I use. And basically, it's an homage to Rush Limbaugh, who passed away some time ago. And I just enjoyed watching him since 1987, basically, when he was on TV, and then listened to him through the radio for years. So I love politics. I disagree with him on a lot of things, obviously, or did disagree with him on a lot of things. But the main thing is, I liked him, and he got me excited about politics and got me paying attention to it. So one of the things he always did was said, us teachers are communists. So my mnemonic for the electromagnetic spectrum is great excess undermines various industries, Marxism rules. So great excess, that be gamma rays, X-rays, undermines various, so that's ultraviolet, visible, industries is infrared, Marxism rules is microwave, and then radio. So all of those parts are parts of the electromagnetic spectrum. They're all that same sort of form where you have an electric field oscillating up and down, a magnetic field oscillating right and left, and then a propagating wave going forward. The only difference between, for instance, gamma rays and X-rays is gamma ray has a slightly smaller wavelength than X-ray does. X-ray has a slightly larger. And there's not a clearly defined end of the X-ray and beginning of the gamma rays. Various groups sort of call it A, but then another group will call it B, and then another group will call it C. So there's not clear definitions that anybody in the world has decided upon to say this is where the gamma rays start and this is where the X-rays end. So it really is a continuum, and you might even run into some arguments where people will say that's an X-ray, and then another group say no, that's a gamma ray, and then another group will say, well, that's an ultraviolet. So, anyways, but that's what the radiation is. So I'm first going to give you an introduction to how heat flows. We're not going to do anything with convection because you can imagine having actual fluids mixing and raising and giving off energy and then falling back down. That's a really, really complicated process. So we don't have any real equations for that, but we have concepts about it that you can, of course, learn, and you'll see in the practice tests and stuff of that sort. But we do have some equations that represent conduction and equations that represent convection. So that's what I'm going to go with now. So I'm going to tell you again, one, the three types of heat transfer. And they are, one, conduction. And I'm going to say touching, just to remind you. And then two, convection. Oops. So that's fluid as an intermediary. And then there's radiation. And for this one, I'm going to remind you, great excess undermines various industries' Marxism rules. That's the electromagnetic spectrum. And I'll also say that you can look at it like this. You can say, I'm a little tilted here in my drawing, but you get the idea. So that's what the electromagnetic radiation looks like. Okay. So the equation that you really need for conduction. Now, you might suspect exactly the right law, but what we're trying to calculate here is Q over T. So that's the amount of heat per unit time. So amount of heat flowing per second. Okay, that's the quantity. And what you can imagine is, let's go right here and say this is essentially a big heat sink. And let's say
Professor, we're not able to see your screen.
oh, good Lord, thank you. I'm glad you reminded me. I literally would have kept drawing forever, probably. Thank you. I'm drawing a really good picture, and it's really nice, and you will not be disappointed by how awesome it is. Sorry about that. Thank you. All right, hopefully it's coming. Okay, so now what you see is I did write heat transfer. I wrote conduction instead of it's touching. I wrote convection instead of fluid as an intermediary. And radiation, I gave you the great excess undermines various industries' Marxism rules and called that the EM spectrum. And then I did that little drawing of electromagnetic radiation in hopes that you might better understand exactly what it is. This, on the other hand, is something of temperature TH. So it's sort of what we call a heat reservoir. So what you're imagining is that this purple block on the left-hand side, no matter how much heat comes out of it, it's going to continue to have a temperature TH. And then there's going to be, in fact, a blue block over here. And this blue block is going to be another heat reservoir. And in this case, the heat reservoir is one of a cold temperature, T cold, but again, it's a heat reservoir. So no matter how much heat or heat you absorb or lose, it's going to stay at a temperature TC. So you want to figure out, well, exactly how much heat will flow across this. Well, what I'm going to do is I'm going to say this distance from here to here is L, and I'm going to say this little area in here that's actually in contact is area A, and of course, that's also area A there. So let me ask you this. Do you think the amount of heat that flows from TH to TC, do you think that's bigger or smaller if the area is big? So heat flowing from TH to TC through that little solid rod, is that more heat going to flow, the Q over T? Is that going to be a larger quantity when A is large or when A is small?
Will it be larger when A is also large?
Exactly. So that allows us to reach the conclusion that Q over T is proportional to the area. What about the amount of heat that flows per second from TH to TC as it relates to L? Do you think L being big is going to make it less or make it more?
Less.
Less. And that's right as well. So we'd put that as A over L. And then thirdly, do you think it depends, or let's say, do you think more heat flows if TH and TC differ by like 100 degrees Celsius? Or would it be more if it's TH minus TC only differs by 1 degree?
The larger difference.
Exactly. So we'll also say that Q over T is proportional to the difference in temperature. Okay. Now, do you imagine, for instance, if we made that red solid rod, if I made that out of gold, or as an alternate choice, I could make it instead of out of gold, I could make it out of, let's say, cotton. Do you think there would be a different amount of heat flow for gold as opposed to cotton? Probably, right? And that's where we have to take into account the property of the material. And that property of the material is called conductivity. So what we say is the equation Q over T is equal to some constant times, notice it's directly proportional to A. So we're going to write times A times T hot minus T cold. And then all that's going to be divided by L. So this is our conduction equation. And this quantity K is the property of the material called the thermal conductivity. And you can imagine, for instance, it's got to come out in joules per second. And I'm multiplying by meters squared Kelvin over meters. So the meters squared over meters is going to cancel out. So I'm going to say K should probably have units of, let's write this here. K is going to have units of, let's say, joules per second times, now it's got to cancel out that extra M on top, the meter from the area squared, or from the area, which is meters squared, and the L on the bottom, which is meters. So that's going to cancel out and leave an A on top, or excuse me, an M on top that we're going to have to get rid of. So I'm going to have to put a meter down here. And then I'm also going to have to get rid of the difference in temperature. So I'm going to put Celsius degrees down here. So that looks like what our thermal conductivity should have units of. And there is a table. It's called table 19.5. Darn it. So table 19.5. And for instance, K for silver, which is Ag, of course, that's 420 joules per second meter Celsius degree. And remember, a Celsius degree is the same thing as a Kelvin. And the fact that you put it after the degree after the C just means there's a difference in temperatures. K, for instance, for copper, that would be Cu, is equal to 380 joules per second meter Celsius degree. And aluminum would be 200, like that. So that's just a few of the values. Ice has a value of 2, glass has a value of 0.84. Again, joules per second, meter, Celsius, degree, like that. So that's actually one we're getting ready to use. Brick and concrete are about the same thing. And you are supposed to say concrete, not cement. Cement's the glue that sticks the concrete together, just so y'all won't get laughed at in the in the engineering or physics world. Most of the engineering world, that's where they pick on you for that kind of stuff. So you can see all sorts of stuff. Air, for instance, has a value of 0.023. So that's something that comes in really, really handy. For instance, for Windows, which is a calculation we're getting ready to do, specifically, thank God that in some sense, when you have on a regular day like today where there's not much wind, you would lose a lot of heat through your actual windows because glass is actually pretty conductive. But as luck would have it, or as the powers that be gave us, it turns out that in general, when you make a window, there's normally a little layer of air on each side, and that layer of air is a little bit warmer than the outside temperature if it's cold, and the layer of air on the inside is a little bit colder than it is inside where it's warmer. Okay, those two little layers of air actually protect us a lot. Now, if we're having a blizzard or high winds, then that outer layer is not going to be there at all. So your windows are a lot less efficient in that situation. But what manufacturers have done is made thermal windows, which is a pane of glass followed by a wafer of air or some kind of gas in between them, and then another pane of glass. And then you still have the little wafer of air on the outside and the wafer of air on the inside. So it's even more cost effective. But that's basically how conduction works. And to give you a problem that we're going to do, let's compute the heat loss for a window. So this is going to be example 2. So a window is, let's make it a pretty big window. Let's say the window is 4.0 meters. So that's really big. That's essentially 13 feet or so by, let's say 1.5 meters. And is, let's say the glass, or let's say instead of is, I'm going to say, and has glass of thickness, let's say that's going to be a full 6.0 millimeters. Okay. That's going to be a pretty thick chunk of glass. Okay. Normally they're on the order of a couple millimeters. This one's going to be 6, but you could sort of expect that if it's really going to be 13 feet wide, you sort of need some thickness to handle that. And we're going to say T inside is going to be equal to, let's say that's going to be, oops, crap, I hate it when it happens. That's going to be 16.0 degrees Celsius, and T outside is going to be 11.0 degrees Celsius. Okay. Now, that's not a huge range, but you can imagine probably the inside air temperature is probably on the order of 18 Celsius or something like that. And then the air outside probably is closer to 8 Celsius. So I'm trying to account for that little wafer of air on the outside so that we don't get completely scary results that makes everybody go ahead and immediately sell all their windows and replace them. So that's what I'm shooting for here. So what I want to know is how much heat is lost per second. Okay, so here we go. Solution. Q over T is equal to, for glass, we know it's 0.84 joules per second meter Celsius degree. The area is 4.0 meters times 1.5, so that should be 6.0 square meters. Then the difference in temperature is going to be 16 minus 11. So that is, in fact, 5.0 Celsius degrees. And then the thickness is going to be 6.0 times 10 to the negative 3 meters. So I can do all this. I'm going to say 0.84 times 6 times 5, and then I'm going to divide all that by 6e to the negative 3, and that gives me 4,200 joules per second. Now, that's basically 4,200 watt light bulbs. That's a lot. So that's not a ideal scenario. That's again why we do double pane windows. That's again why we're lucky to have a little wafer of air just outside and a little wafer of air inside. And your book will have various examples, as will your exercise, your homework problems. They'll have various examples where you can do multiple layers of stuff, and it'll show you or walk you through how to do that. So does anybody have any questions on that one? Of course, that's a big window too. You wouldn't really normally put such a window on something like your house, for instance, but you certainly would for a business. But that's basically the calculations we do with conduction. Uh, your book also talks about how clothes works to insulate you, so that's something worthwhile reading. Now, I also want to tell you that in the building industry, which, if you're going to be an engineer, at least a mechanical engineer or a structural engineer or a civil engineer, then the building industry is something you got to deal with. So in the building industry, the K is not the most relevant quantity. Does anybody know from any experiences you had, do y'all think you might know what the relevant quantity is in the building industry? You ever done any DIY projects or, insulated a house or anything like that? Okay, what they use is the R value. And what the R value is in terms of what we know is the following. The R value is actually the length divided by the K. And then, of course, that forces us to say Q over T, which was KA over L times delta T. We can now say that is A delta T over R. And for instance, they have R13 for 2x4 walls and R19 for 2x6 walls. And then for your rafters, they have whole sheets that are sometimes like 8 inches thick, stuff like that. They got rock wool, they got all sorts of stuff. And what I want to tell you is that, for instance, R13 means 13 square feet times horsepower, times hours times Fahrenheit degrees per BTU. So it's really nasty, nasty units. R19 is a similar one. That's 19 feet squared times hours times Fahrenheit degrees per BTU as well. But the main thing I want to tell you about that is if you actually use that pink, that Corning type insulation, or any of the other companies that make them, the Pink Panther and that sort of stuff, if you use that insulation, do not be confused by the importance of what they're for. So, for instance, it's not uncommon to see a DIY guy, do it yourself guy, decide that he's going to build this barn or this shed or whatever, and he builds a 2x4 shed because you really don't need 6-inch walls, or it's actually technically 5 1/4, but you don't need 6-inch walls for a shed. But maybe he decides, well, sometimes I get kind of cold when I'm out working, or sometimes I get kind of hot when I'm out working, depending on the weather. So it'd be nice to have a little bit better insulation. So the idea might be, hey, I'm going to, instead of using R13, I'm going to use R19. Well, if you do that, it turns out, and the building inspector will ping you on it and actually make you rip out all that insulation. It turns out that if you take R19, which is made for basically studs that are 5 1/4 inches thick, and you compress it down to 3.5 inches thick, which is what 2x4s are. 2x4s are only 3.5 inches thick. It ends up that the R value of the R19 shrinks down to less than 13. So it will fail inspection, but not only that, you've spent more money on R19 to get less than you got when you did R13. So just keep that in mind. And the main reason why is because fiberglass is not that great of an insulation. Fiberglass, it's decent. For instance, I'll give you the K value from the table. It's just as soon as it pops up. So I think they give it, yeah, fiberglass is 0.048. That's pretty good. It's more than twice as much as air, though. That's the key point, because fiberglass is sort of ephemeral. It's if you put a pile of fiberglass, there's a lot of air gaps in it. Those air gaps are really what's important. So when you compress R19 down to 3.5 inches, you've squished out all the air, and now you're not getting the benefit of the 0.023 K value that air has, because you've squished out all the air. So that's why you don't use that. Any questions on that one? All right. I know I owe you guys a break. Actually, no, I can go ahead and do that. Let's go ahead and take a 10-minute break. It's going to take me about 10 minutes to finish this chapter off. So let's go ahead and take a 10-minute break. And then I'm going to finish the chapter, and I'm going to jump into chapter 20 and give you the entirety of what we need for chapter 20. So come back at 7:10. I will be right here in case anybody has any questions. But thank you for bearing with me for this whole hour and a half already. Do not. Good. Well, I mean, I'm just going to take it in a few. So, whenever you get a chance, no rush. All right. Let's do this. Now I got to check some stuff while you guys are here. I'm going to check some stuff in Canvas to make sure everything's up to snuff. Yeah. I'm adjusting the homeworks. I'm giving you guys a little bit more time in case some people missed chapter 18. I gave more time on that. Hopefully that'll help you guys. But got about 2 minutes left, everybody. All right, got 1 minute left, folks. right, so now it's time to get back started. We're looking right now at the stuff I just talked to you about regarding conduction, specifically the R values that are used in the construction industry. I want to go ahead and put a little line ending that. What I want to tell you is I just changed the dates for the chapters 18 and so on. So if you got a chance to do chapter 18 and you already did it, that doesn't apply to you at all. But if you didn't finish it, or maybe you wanted to take a couple more chances to get a better grade, now I've made chapter 18. Oops. I've now made chapter 18 due on, this will be conceptual and then the homework. So it's due on the 9th. So I'll say ditto for, because they're both on the same time. Then chapter 19. First is the conceptual. Chapter 19 I made 612. And then chapter 19, part 1 and part 2 are 617. And then I made chapter 20. That's actually now chapter 20 conceptual is 617. And chapter 20 homework is 619. So those are all the due dates. Anybody have any questions about that? All right, so we got that finished. Now, the next thing that we're going into is, in fact, radiation. And the same quantity is being used. It's the amount of heat per unit time. So we're going to talk about radiation here. Oh, man. If you actually use this app and you do the little thing where it automatically makes your circles into perfect circles and your lines into straight lines, and you handwrite it, it'll just make it into scribbles. So that's kind of awesome. Not helpful at all. But anyways, there's something called the Stefan Boltzmann law. And the Stefan Boltzmann law, that's by the way, 2 M's, are the Stefan Boltzmann equation. God darn it. This is very important, for instance, in astronomy and astrophysics. And in astronomy and astrophysics, they would call the quantity Q over T. They call that the luminosity. Specifically, they call it the luminosity for a star. The Q over T for other things isn't necessarily what you call luminosity, but that's what they call it for a star. And they use the symbol L. And here we're using the symbol Q over T. And it turns out that that luminosity, which is the amount of heat flowing per unit time, is in fact directly proportional to the area. That's the surface area. So if you're talking about a star, stars are generally, that's not necessarily the case in all of them, by the way, but in general, stars are spherical. So the surface area would be 4 pi r squared. But that's what we mean by A. And it's also proportional to the temperature to the 4th power. Okay. Now, surface area normally means A equals 4 pi r squared for a star. Again, there's some stars that are actually quite elliptical. R, area is proportional. I shouldn't write it that way. Area is proportional to r squared. So that's the general consensus. So you can think about this as luminosity, in which case it's quite abstract because we're talking about how much heat a star puts out per unit time. And that's a very abstract quantity. It's not something you can physically see. But if you think in terms of electric burners on the stove, you have the electric burner that's like this big, and then you have another one that's like that big. If you take a pot that's as big as that big burner and stick it on that small burner, you know for a fact that it's going to take a lot longer time to bring that pot of water to boil. So it should make some sense that the amount of heat that flows in that instant from an electric burner to water is directly proportional to the area of the electric burner. And that's why it's here. And because area goes like in the case of a circle, it'd be the square of the radius or the square of the diameter. But the main thing is it goes by the square of some measurement. So the bigger the area, if you double, for instance, the radius, then you actually quadruple the area, and therefore you can actually put out 4 times as much luminosity or heat per unit time. Then the other variable is the temperature, which is T to the fourth. So that is a really big deal because, for instance, I will give you a little example. I'm going to tell you basically it is proportional to A and T to the fourth, but it has something called the emissivity, and it also has sigma. That's the Stefan Boltzmann constant. So this is called the Stefan Boltzmann constant. Well, that's very good. And the Stefan Boltzmann constant is 5.67. Ah, dang it. If anybody can tell me how to make my iPad stop doing that, I'd be really tickled to hear it. I haven't been able to find anybody yet, so it just keeps erasing when I don't write very much. So that's watts per square meter per Kelvin to the fourth power. That's what the Stefan Boltzmann constant is. And the epsilon is the emissivity, which is a measure of how reflective versus absorptive it is, or something like that. So we're going to say this is the emissivity. It's something generally that they have to give you. That's one way of thinking about it. And it actually has one M, not two, but it does have two S's. So EMI, dang it, there it goes again. EMISSIVITY. Okay, so that's the actual Stefan Boltzmann law. So let me give you an actual neat story. So if you look in the night sky, you will see, and in fact, this one's kind of cool because it looks more red than really blue. And then there's another star over here, and there's another star over here, and there's some stars right here, and there's a star right here, and there's even some stars out here, and a couple little stars right there. So these are all stars, and in fact, what I'm trying to show is the brightest stars are the ones with the biggest view. Does anybody recognize this star pattern? I suspect most people do not, but if anybody's even remotely interested in astronomy, you would know. Anybody know what this is? That's Orion the Hunter. Okay. This star right here is Michael Keaton. Anybody get that joke? So that's Betelgeuse. Okay. That actually comes from an Arabic word that's been interpreted as shoulder or even armpit. Betelgeuse, and it's a very different spelling. And of course, we're transliterating when we spell this in English because the in Arabic you don't even use the same alphabet as we do in English. So it really is some freedom in how you choose it. I actually wrote it like beetle, the bug, followed by orange juice. And I don't care that you know whether the proper spelling is or whatever. This other star over here is called Rigel. Okay, and that's a blue star. And in fact, this star, Betelgeuse, has a temperature that's on the order of, let's say, 4,000 Kelvin, whereas Rigel has a temperature that's on the order of, let's say, 30,000 Kelvin. Okay, Now, it turns out that Betelgeuse is also called Alpha Orionis. And Rigel is called Beta Orionis. And the reason why is alpha is the letter that you use for the brightest star, and beta is the second brightest, and then gamma is the third, and delta, and so on and so forth. So it turns out that Betelgeuse and Rigel, Betelgeuse being red and Rigel being bright, bright blue, they both looked about the same, but everybody hands down thought Betelgeuse was the brightest of the two stars. So they named it a long time ago Alpha Orionis. And once technology came online for where we could actually tell what the temperatures were, it turned out that actually Rigel is actually a little bit brighter. But the main thing is the fact that they're so close that they mistake them tells us that the luminosity, which is really related to the brightness, that luminosity for both of those stars are very, very close. Now, in addition to that, the luminosity is the total amount of energy put out by the star, whereas the brightness is the total amount of energy put out by the star divided by divided by 4 pi r squared, where r is the distance away from us. That makes sense, right? A 100-watt light bulb, if you put it right up against your eye, it could burn your eye out because it's very, very, very bright. Whereas you could take it and put it a mile away and you barely even see it. So it turns out that brightness, B, is equal to luminosity, and then that luminosity is equal on any sphere centered on that star. So the brightness is 4 pi, and I'll use d so you recognize it as distance. The brightness is 4 pi over d squared. Now, something else that's interesting about Orion is that Orion, unlike a lot of the stars, Orion is one of the few stars that is actually the most of the brightest stars in it were made in the same nebular cloud. So that means all those stars, just about all the brightest ones that you see in Orion, are all about the same distance away because they were all created in the nebular cloud. And nebular clouds are big. They're like, it's not uncommon to have a nebular cloud be a couple light years across. But when you're talking about a star system that's on the order of 1,000 or 2,000 light years away, a couple light years is really minuscule, so you don't have to think about it. So in addition to the brightness of Rigel being approximately equal to the brightness of Betelgeuse, which I'll just call, well, I could have thought of something better than that. I'll just say brightness of Betelgeuse. Okay, since they're about the same, and D Rigel is about the same as D Betelgeuse, then that means when you look at those two stars, you're actually comparing their luminosities. So those two facts combine to say that L, the luminosity of Rigel, is approximately equal to L, the luminosity of Betelgeuse. Okay? Now, that leads to a big question. The temperature of Rigel is about, let's say, 30,000 divided by 2 would be 15,000, divided by 4 would be 7,500. So the temperature of Rigel is about 7,500 times the temperature of Betelgeuse. And luminosity goes like T to the fourth, which would mean that the luminosity of Rigel should be on the order of 7,500 squared, or excuse me, to the fourth power, which is 3.1, about 3 times 10 to the 15th. times the luminosity of Betelgeuse, just based on temperature, right? But we know for a fact that they're comparable. The luminosity of Rigel and the luminosity of Betelgeuse are about the same because they're the same distance away. And since they're the same distance away, when we're looking at their brightness, which is what we can tell with our own eyes, their brightnesses are about the same. But because they're about the same distance away, that means their luminosities are about the same. So how can we account for Betelgeuse and Rigel being about the same luminosity if the temperatures would make them be, for instance, Rigel about 3 followed by 15 zeros times brighter? Can anybody tell me what would make Betelgeuse be able to be so bright?
This is just a guess, but like different elements they're composed of.
That actually plays a role in a lot of stuff, but it's not in this one. Look at your formula, but thank you. Look at your formula for luminosity. What does that depend on? And give it another try, either Ethan or anybody else. So the total amount of light output by a star, for instance, or anything, according to the Stefan Boltzmann law, it depends on obviously the emissivity. Doesn't matter too much because, you know, obviously whatever is cloaking the star is the same for Rigel as it is for Betelgeuse. So we expect the emissivities to be somewhat comparable. The sigma is a constant, so that can't be anything. The temperature is raised to the fourth power, but what else does the luminosity depend on?
Area.
Right. So the only way we can account for Betelgeuse being about the same brightness as Rigel is by assuming that it must have a much larger surface area. But here's the crazy thing: surface area goes like R squared. So temperature goes like T to the fourth. So R is going to be a lot bigger for Betelgeuse to try to compensate for that 3 times 10 to the 15th. So for instance, if you take the square root of 3 times 10 to the 15th, you get square root 3 e to the 15. You get about 5.4 times 10 to the 1, 2, 3, 4, 5, 6, 7, are about times 10 to the 7th. Okay. So that means the Rigel, the star, which might be a big star, might be a small star, but the main thing is compared to Betelgeuse, it has to be teeny because Betelgeuse is going to have to be about 10 million times larger in radius. And it turns out that that's exactly the case. In fact, Betelgeuse is so big, its temperature is pretty comparable. It's a little colder than our sun. It's what we call a red supergiant. And in fact, it's so large that if you replaced our sun with it, not only would it be way bigger than our sun, it would be so big that the orbit of Mercury would be inside of it, the orbit of Venus would be inside of it, and then the error bars on our knowledge of this suggest that it could even possibly be bigger than the orbit of the Earth. So the Earth might actually be inside of it as well. So yeah, that's actually an excellent example of how the Stefan Boltzmann law works. There's 2 ways you can deliver more heat. One is by for instance, if you're trying to warm yourself up by leaning against a hot piece of metal, as much surface area of your body that you can get up against that hot piece of metal, that means more heat's going to be delivered to you. If you saw that episode of Big Bang Theory, when Leonard, Rajesh, and Wolowitz and Sheldon all went to the North Pole to do an experiment, they lost power one night and they had to all strip down naked and lay inside of a inside of a sleeping bag together. That's because you don't want your clothes interfering and insulating you from your neighbor. You want each other's full skin contact to actually allow the full surface area of the body that's touching to actually conduct heat to you. So that's what's going on with this. Is just like the conduction part, the area is directly proportional to the energy delivered. So yeah, that's why we would choose to lay next to each other naked if you had to save your life. Okay. I didn't know that's where we're going today, but that's where we went. So now let me actually show you another problem. Now that I've introduced the Stefan-Boltzmann law, I will tell you that in fact, everything that has a temperature greater than 0 Kelvin radiates heat. And that radiant heat is given by epsilon, which is the emissivity, times sigma, which is the Stefan-Boltzmann constant, times the surface area of that thing, times the temperature of that thing to the 4th power. That's how much radiation it's going to emit. But that thing is immersed in an atmosphere, and that atmosphere, if its temperature is greater than 0 Kelvin, which it is, it's going to give off radiation as well, and that's going to be absorbed. So if you want to actually calculate the total amount of energy or the net radiant heat flow for a particular object, then the equation becomes a little bit more complicated. You can say Q over T is equal to the emissivity again times sigma times A times T1 to the 4th power minus T2 to the 4th power, where this is the temperature of the surroundings. And this is the temperature of the object. So, and in fact, it also shows you that if the surroundings and the object have the same temperature, then the heat flow will be 0, which is exactly what we expect because it takes a difference in temperature for heat to flow. So that's another expression we can make use of. And that's what we're getting ready to do now. So we're going to work this will be example 3. So for example, C3, what we want to do is imagine an athlete sitting unclothed in a locker room. There we are with naked again. So an athlete is sitting unclothed in a locker room whose dark walls are at a temperature of 15 degrees Celsius. Estimate the body's rate of heat loss by radiation, assuming a skin temperature of 34 degrees Celsius and an emissivity of 0.70. So this is exactly example 19-17. And what we're told is that the area of the athlete is supposed to be about 1.5 square meters. The emissivity of the athlete is going to be about 0.70. The temperature, which we'll call T1 of the athlete, is actually 34 degrees Celsius. And the temperature T2, which is of the surroundings, those black walls and whatnot, is 15 degrees Celsius. What I have to tell you, though, is T must be in Kelvin. I should have put that here, but I will remind you now. T must be in Kelvin. Okay, same thing with this formula. T must be in Kelvin, just like the ideal gas law. Okay, so we can go ahead and calculate this. Q over T is equal to epsilon sigma A T to the 4th minus T to the 4th parenthesis. So this is going to give us 0.70 and then 5.67, double checking my number, 5.67 times 10 to the negative 8. And that is watts, which is joules per second, per square meter, Kelvin to the 4th. And then times the area, which is 1.5 square meters. And then times, we have to put it in Kelvin. So what this is going to become is T1, which is 34. If I add that to 273, that's going to give me 307 Kelvin to the 4th power minus 15 plus 273 is 288. So that's going to be minus 288 Kelvin to the fourth power, close square brackets. So I'm going to say 307 to the fourth. Enter. Now I'm going to do minus 288 to the fourth. And this gives me 2.0032 times 10 to the, so this is just this quantity right here is 2.0032 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the ninth Kelvin to the fourth. That's that number. Now I'm going to multiply that times 0.7 times 5.67 e to the negative 8. And then times 1.5. And that gives me 119. Oops. That gives me 119.3. And notice the way the units work out. The emissivity has no units, but we have watts per square meter times a square meter. So that cancels out. We got T to the fourth, which is Kelvin to the fourth, and then Kelvin to the fourth in the bottom. So that cancels out. So this is just watts. And in fact, we only had 2 sig figs. So technically, these two numbers aren't right. And we're going to say this is approximately 120 watts. So you can see that actually your energy loss, just sitting there in the locker room, say, where the temperature is like 15 and your body temperature is normal body temperature, you're losing about a little bit more than a 100-watt light bulb loses. And of course, if you sit there long enough, you will go into hypothermia. Not only that, your body is actually, stealing some of that energy too. So you're not only losing energy by heat going to the environment, you're also losing energy by heat that from the food that you've ingested is being used to power your brain, to power your heart, to power your lungs, to power your muscles. Even if you're sitting perfectly still, you still have all the other stuff going. So that's actually what it's like. And this is also the reason why when you go to, for instance, a high school basketball game, when you first get in the gym, especially if you're early, it can be quite chilly or whatever, or at least it's going to be a normal temperature. But as soon as the place fills up, it starts getting hot and uncomfortable because basically every human in there is like a 100-watt light bulb. This one's 120 because it was a little more extreme, but in general, each human puts off about 100 watts. So if you get, 3,000 people in there, or, if you're at the Dean Smith Center, it's like 23,000 people. That's obviously 23,000 100-watt light bulbs, and you're going to get warm. Luckily, that has a huge open air above it, but a high school gym's quite different. Anybody have any questions on that? All right, so we've now finished chapter 19. So I don't like offering a physics course in which we cover thermodynamics, but which we don't do the second law of thermodynamics. But it turns out that's quite normal. That's been what we've been doing at TCC for some time. I'm just not liking that. So I continue to cover chapter 20, but I do so in a very short cursory way. Basically, I can't justify teaching a thermodynamics course without the second law of thermodynamics. And chapter 20 is called the second law of thermodynamics. So let me give you a little rundown on exactly what you need to know about that. Notice that I'm going to actually truncate the amount of stuff you can know. I still want you to read the chapter and do your best with the homework set. But on the test, I'm going to give you a quite narrowed down area of questioning for it. So chapter 20 is the second law of thermodynamics. Oh, I wrote an E on there. So that's the chapter we're going to. And what I want you to know is basically the most important thing I need you guys to get from this is the various versions of the second law of thermodynamics. I want you to be able to calculate the Carnot efficiency, which is a simple, straightforward formula, and I want you to be able to use that. But I also want you to know the definitions of all the various versions of the second law of thermodynamics. So that's what I'm going to go over here. So if I turn to section 20-1, they open up with a nice little story. And the story is basically, imagine you have a cup of coffee. So let's stop sharing the screen for a second. Let's imagine you have a cup of coffee, or let's say a cup of tea or whatever. But imagine it being in like a porcelain cup. So that's a little more helpful. But you can imagine a scenario where my cat jumps on the table, knocks over the cup of tea or cup of coffee, and it falls on the floor and breaks up into hundreds of pieces, and tea is everywhere and all that sort of stuff. Well, according to the first law of thermodynamics, which remember is just conservation of energy, you can actually have all that coffee that spilled spontaneously jump off the ground and land in the area where the cup started to break. And all those pieces of the cup can jump back together and stick together to form the exact same shape of the cup. And then the cup can launch itself up onto the table. And that would not violate the first law of thermodynamics, which is, again, conservation of energy. So that's a problem. We know that never happens. It never happens, right? There's other things, of course, that never happen. For instance, I can take and rub my hands on this desktop, and slowly my hand and the desktop will get warm. Now, imagine this. What if I were to lay my hand on here and then spontaneously the table starts to get hot, and that heat sucks out of the table and goes to my hand and forces my hand to move back and forth? That doesn't happen either. In fact, statistically speaking, it's a very, 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 very low probability that it would happen. And that's sort of where we're going with the second law of thermodynamics. The second law of thermodynamics is the law that says, yeah, glasses fall off of tables and shatter and make a mess. But even though conservation of energy is not violated and the first law of thermodynamics is not violated, coffee cups do not reassemble themselves and jump back on a table. So in some sense, you can look at whatever that disorderly conduct was, that is a measure of what we call time zero. That quantity is ultimately going to be called something that we call disorder, which is technically named entropy, E-N-T-R-O-P-Y. That's the entropy, and that involves us with another version of the second law of thermodynamics. So that's what we're trying to address with the second law of thermodynamics. So first off, I'll write the first law of thermodynamics is conservation of energy.
Could you share your screen again?
Yeah, will do. Thanks, bud. Man, it's like you're just working with a genius here. Okay, so let's do this. I'm going to share screen again. And all I've written down so far is just chapter 20, second law of thermodynamics. And the first law of thermodynamics is, in fact, also called conservation of energy, which we learned about in chapter 19, of course. Oops. Specifically, what we learned was delta K plus delta U plus delta E internal is equal to Q minus W. That's the first law of thermodynamics. Now, the second law of thermodynamics has a lot of different forms. And when we're reading over our book, it tells us about the second law of thermodynamics. It tells us about the first law of thermodynamics. It tells us about that cup not being able to work backwards. So, in fact, the Clausius statement, and that's Clausius, C-L-A-U-S-I-U-S statement, is that heat flows spontaneously spontaneously from a hot object to a cold object? So that's the first law, or the second law of thermodynamics in the first form that I gave you. Heat will not flow spontaneously from a hot object to a cold object. So that's one version. And in fact, you might be able to think of heat flowing from a cold object to a hot object. So, for instance, in your refrigerator, the air is quite cold. But what your refrigerator does is it removes the cold air in the refrigerator and puts it into the hotter kitchen. That's basically what looks like a violation of the second law of thermodynamics, but it's not a violation of the second law of thermodynamics because it's not doing it spontaneously. In fact, you have to pay an electric bill to make that happen. So you can actually overcome the second law of thermodynamics and force heat to flow from a cold object to a hot object, but it doesn't do it all by itself. So imagine a scenario, for instance, where you put in an ice cube into 20 degrees Celsius water, and normally what would happen is the ice cube would melt and become water, and then the water and the original cup of water would reach equilibrium, let's say at like 18 degrees Celsius. That's a very normal problem. That's spontaneously heat flowing from a hot object, specifically from the warm water in the cup to the cold ice. That's spontaneously happening. But according to conservation of energy, you could also have just that whole cup of water that we just finished with, spontaneously heat could leave the actual chunk, big part of the water that's in the glass, and that heat could leave such that it actually heats up the water and freezes itself and makes an ice cube. Okay, that's not violated by conservation of energy or the first law of thermodynamics, but it is violated by the second law of thermodynamics. So that's one version of the second law of thermodynamics. Your book then talks about a heat engine. We've only got a couple minutes left. A heat engine is basically something that extracts heat from a hot reservoir, takes some fraction of that heat and does some useful work. And then the remainder of the heat, which has to be some, in other words, that's another version of the second law of thermodynamics, is there's no heat engine where some heat is not wasted. So some of the heat will be wasted, and that's delivered to a cold reservoir. We're going to teach you that one of those engines is in fact a Carnot engine. And when you do that with a Carnot engine, you can calculate the efficiency, and that efficiency allows us another way of stating the second law of thermodynamics, which I'm coming up with now. So, nope, not there, not there. I'm actually, okay, second law of thermodynamics, this is the Kelvin-Planck statement. So the Kelvin-Planck statement, basically says, no device is possible whose, I learn it, sole effect is to transform heat, or transform a given amount of heat into work, completely into work. So that's another version. And ultimately, all of these are going to turn out to be identical. In other words, we can prove that one is the same as the other, is the same as the other, and so on and so forth. So that's the Kelvin-Planck statement. There's other ones as well. There's also a third law of thermodynamics that you should know, because there literally could be a multiple choice question that has, or a multiple pick question that has various statements, and then you have to identify which one's the first law of thermodynamics, which one's the second law of thermodynamics, which one's Newton's first law, which one's Newton's second law, which one's Kepler's third law, which one's the second law of thermodynamics, third law, all that kind of stuff. So all that's fair game. I just wanted to point that out to you. Another version of the Clausius statement is no device is possible whose sole effect is to transfer heat from one region at temperature TL into a second region at temperature TH. So that's another Clausius statement. And again, all of these have been proven to be equivalent. We'll talk more about it next time, but I just want to get through these other versions of the second law of thermodynamics. Another version of the second law of thermodynamics is involves entropy. And I'm looking for that particular version, but basically the entropy of the universe always increases. That's one version of it, but I'm trying to give you the one that's in the book. I'm looking. Okay. The entropy of an isolated system never decreases. It either stays constant for reversible processes or increases for irreversible processes. So that's the second law of thermodynamics. It's called the general statement of the second law of thermodynamics. The total, and here's another version of it, the total entropy of any system plus that of its environment increases as a result of any natural process. So that's another version. Your book also talks about time zeros. That's another version. And natural processes tend to move towards a state of greater disorder. That's another version. And you can just go through the book and look for these in bold print, but that's mainly all I wanted you to do. In any natural process, some energy becomes unavailable to do useful work. That's sort of treating heat as if it's a bastardized version of energy. And then finally, there's this cool thing that we learn, and it's basically that the entropy S is equal to Boltzmann constant times the natural log of W, where that W is actually called the number of micro states corresponding to a given macro state, which is really phenomenal that that's true. So if you guys just read chapter 20 and sort out this, I'll talk about it more next time. You're all free to go. I'll wait here for the last person to leave in case anybody has any questions, but thank you everybody for coming. And sorry I ran over by 2 minutes. Okay, I'll see if I can give you back 2 minutes next week. Have a good weekend and stay safe. Oh, that was it.